Uh, Today I will be dealing with another interesting topic on spectroscopy, and this is one of the spectroscopic tool widely used in many research labs. However, considering our own limitations for getting such a sophisticated spectroscopic tool, in our country we have not really majored on this spectroscopy. Therefore, I would like to singly emphasize more about the usefulness of this spectroscopic tool, which has come into the study of materials in a bigger way. This is popularly called as X-ray absorption spectroscopy, and this is also complementary to whatever information that we are getting from X-ray photoelectron spectroscopy, which we have seen in the previous lecture, where we have highlighted that XPS spectroscopy is or XPS spectra is a very good surface analysis tool, where up to 10 nanometer thick surfaces can be studied in greater detail, talks about the impurities that can happen in the surface, and then how we can probe the different metal ions that are present, and also on the characteristic X-ray that is coming out. Therefore, XPS is a very good analytical tool, but today what we are going to see is a absorption phenomena which has been used very nicely to explore unusual oxidation states. So, in this lecture I will give you some principles about how X-ray absorption spectroscopy can be understood, and then little bit on the instrumentation, and I will take one particular group of oxide and do a thorough study on how we can use excess information for analyzing a particular perovskite compound. As you would see, the incident rays that are falling on a sample actually is undergoing a lot of change. One is you can get scattered X-rays from the sample, or we can get fluorescent X-rays which are used for X-ray fluorescence spectroscopy, or we can get photoelectrons. The light can also be transmitted, but not in the same magnitude of that of the incident ray, and therefore we can try to map the intensity ratio as a function of mu x, and x is your thickness and mu is your absorption coefficient. So, if your sample is sufficiently thin, it is possible even to map the transmitted X-rays, and the phenomena that is happening when X-rays are absorbed by the sample, it can either come out as a photoelectron or as a Auger electron and then a fluorescent photon. So, from the way we harvest the secondary processes that happen due to the interaction between the material and the incident X-rays, we can categorize different sort of spectroscopies. In the last lecture I showed the same view graph, where I characterized two important techniques. One is based on electron spectroscopies and one based on ion spectroscopies. Especially I talked to you about Auger electron and discussed to you in detail about X-ray photoelectron spectroscopy, gave you some idea about RBS, which is specially used to look at epitaxial layers and how the thin films are growing as single crystals. Also I told what this X-ray photoelectron spectroscopy is. Basically this is reflecting a photoelectric effect, and this simple photoelectric effect can be transformed or exploited to analyze and quantify several chemical reactions, and there we looked at what this photoelectric process is. The ejected photoelectron is what we are trying to map, and in the process you also have the Auger electron that is coming out from here. Now, to draw a parallel between XAS and XPS, I just want to make some comments. One is core holes are created anyway when a core electron is actually knocked out, and therefore by ionization it can happen, and that forms the basis for X-ray photoelectron spectroscopy. Core holes are created by ionization by the incident X-rays, and therefore those are called as X-ray photoelectron spectroscopy, and core holes are formed by excitation of electron, which forms the basis for the X-ray absorption spectroscopy. So, in both cases XPS and XS, we can say that the final states are highly unstable and the core hole decays by non-radiant process. One is either a Auger relaxation, which ends up in a Auger electron spectroscopy, or by radiant X-ray emission process, which is called as X-ray emission spectroscopy. So, this X-ray emission spectroscopy is actually a secondary phenomena that goes along with XS, whereas AES is a secondary phenomena that happens because of XPS. So, in some sense both have a parallel. So, when we talk about XS, we also take into consideration X-ray emission that is coming out. To make things look simpler, how do we get this absorption spectra? We can say that there is a beam of different wavelength. You can use any sort of a wavelength, and this beam source is actually incident on the radiation, and now the electron is actually absorbs energy, and it can go to any of the bound states or to any of the states near to the continuum, that is the vacuum level, or it can go into the vacuum level, and depending on that then we can try to populate those regions selectively, and then the transmitted radiation can be mapped, and this is what comes out as a absorption spectra, which we can try to analyze. Now, there are two things that we need to have in mind. One thing is, when in X-ray absorption spectroscopy, if we have a core electron which is excited into unoccupied atomic or molecular orbitals above the Fermi level, then XS can be divided into two regimes. One, we can call this as X-ray absorption fine structure, or we can call this as extended X-ray absorption fine structure, when the outgoing electron is well above the ionization continuum. But if it is somewhere in the bound states, for example, we talk about a 2p going to 3D level or 2p to 4D level, then we talk about bound states and low energy resonances in the continuum. So, either of this can happen. As you see from this view graph, electron is knocked out and it is actually going above the Fermi level, but it is not actually going into the continuum. So, this is one of the bound states, and depending on that, you will get a typical characteristic feature of X-ray, which will tell what sort of excitations are possible. In this case, you can see nitrogen is absorbed on nickel 100, and when it is glued or to the surface, when it is adsorbed to the surface, then you get a clear reflection for a 2 pi interaction, and this is a typical XS peak that you would get for nitrogen 1s to 2 pi transition, 2 pi star transition. We will come to this issue in example. So, just to map what are all the different studies that we can do in XS, we can actually talk about a pre-edge, which is which can be characterized here as X-ray absorption near edge structures, XANES, and this is what is the region where you can actually map the information that you are getting. In fact, you would get several features around this edge. So, this is what you call it as X-ray absorption near edge structure, and this is the region where you actually play around for X-ray absorption spectroscopy. I will tell you what sort of peaks that you can get out of this, and this is the region where you have the transitions happening between 1s to n plus 1 p level, or it could be p to n plus 1 d level. So, this region actually takes care of such bound states, and this is the region where you can talk about the pre-H. And if you are talking about 1s electron knocked out of the continuum, or if the knocked out electron is well within the continuum, then you talk about the extended X-ray absorption fine structure. So, several of these processes happen, all these are mapped under the same phenomena of X-ray absorption spectroscopy. So, we will specially look, it is not possible in one single lecture to cover the whole spectrum of manifestation of this spectroscopy. So, I would like to take some interest to talk about different things that can happen in this H. That is why it is called as H spectroscopy, and this H is actually attached to the sort of excitations that can happen. It can be called as KH or L or M. We will see that in the next slide. As I told in the previous one, we are talking about different forms of spectroscopy here, and this is the XSH spectroscopy that we are precisely talking about, and the relative scale of energy that involves each of the spectroscopy is also given. Therefore, we can single out and say that I am exactly talking about XFs, or I am talking about XANES, or I am talking about XS based on the energy range that we are using for these spectroscopies. Now, when we talk about H, we are talking about different transitions that can happen, absorptions that can happen. If KH is happening, then the electron from 1s is actually excited, and therefore, we call this as a KH. If it is L, then it can involve both 2s and 2p, but we differentiate that between L1, L2 and L3. L1 is typical for 2s electrons getting to the continuum, or it could be 2p or 2p 3 by 2. So, both these are characterized by L2 and L3. When we actually talk about bigger metal ions, this L2 and L3 give a very rich information about the oxidation states. Similarly, we can go for M1, M2 and M3 so on. Each one is designated by the orbitals that are associated with it. So, XS data are obtained by tuning the photon energy using a crystalline monochromator to a range where core electrons can be excited, and the range is typical of the order of 0.1 to 100 keV photon energy. Depending on the range, then we can selectively try to knock out the particular core electron. So, if we talk about K, then we are talking about a very high energy radiation. If we talking about 2p levels, that is LH medium range, and then still smaller ranges for 3D, 3s and 3p. So, this is how we designate this KH, L1, L2 and L3. L2 and L3 we try to categorize based on the LS coupling. So, if your transition is from P to D or S to P, then your L is equal to 1 and this 1 can couple with either S is equal to half or S is equal to 0, and depending on that you will actually get this half or 3 by 2, which is nothing but your LS coupling. So, based on this you can get L2 and L3. Always we can remember as a notation L3, we always talk about 3 by 2. It is easy to remember that way. L2 is half. So, L2 L3 edges are nothing but two states from the same transition resulting out of the spin orbit coupling. Typically, if you look at X-ray map, XS mapping, you can see a sharp edge for K, and this is for L1, this is for L2 and this is for L3, and as you would see here, L3 always comes at higher energy compared to L2. So, in a typical spectra of XS, your higher energy spectra will always be associated with L3, and the low energy peak will be associated with L2. And there are other things that happen apart from the H, where you have for example, this platinum tetracyano complex, where you see additional features that are coming, and these are called the near edge fine structure due to excess, and this peak comes from a constructive interference, and this peak comes from destructive interference. So, these fine structures can give us idea about the local coordination and other informations about bonding and the nearest neighbor occupancy and so on. So, this is also a very useful tool that is being probed. Now, where is XS becoming more crucial and more sophisticated, as I mentioned to you, the way we produce X-rays are very typical. We use filament to get electrons which will knock at a particular target, which is copper, molybdenum or any particular metal, and when it strikes, characteristic X-ray comes out of it, which we categorize as K alpha or K beta radiation. But in synchrotron radiation or in XS, we actually get a high energy X-ray and not the conventional one that we generate in our usual lab practices. What we do here is get the same X-ray, and this X-ray is actually confined to a ring, and in this ring we try to boost the speed of this electron such a way it is a accelerated electron which will X-ray beam which will actually come out, and that will collide with your material to have a very selective excitations made. So, what we are trying to do is generate the same X-ray as that of the lab experiments, but we are trying to accelerate in a confined space. So, this is your conventional X-ray machine. X-ray comes, it interacts with your material and then it goes to the detector. In synchrotron source, we actually try to boost the speed of the electron, and then the X-rays are X-ray beam is actually brought out with a greater force. So, one of this can selectively go and hit. So, when it is actually spinning at different points, you can collect the X-ray beam. Therefore, this is called a synchrotron, because in one space you can have many stations where you can try to get it with the different centrifugal inclination. At different tangents you can try to get the source output, and as a result we can study from one synchrotron source many experiments parallelly. So, this is that way a very sophisticated instrumentation, and just to show you, one of the major facilities is in Germany, it is called DESI, and there is another one is called BESI in Berlin, and DESI is in Hamburg. As you would see here, it is more of a consortium, it is not a single man's property. Most of the research institutes, foundations including government, they pitch in to sustain such a major facility. Therefore, this is not a simple stuff. Definition of a synchrotron, we can take it from here. When high energy particles are in rapid motion, including electrons, they are forced to travel in a curved path by a magnetic field, which we call it as booster, and then synchrotron radiation is thus produced. We will look at bird's eye view of one synchrotron facility which is there. This is your linear accelerator. I will also show a animation in the next slide. This linear accelerator actually pumps in X-ray, which is actually getting boosted here with a magnetic coil, and then on gaining momentum this will actually go into the outer sphere, and then from here at different points you can actually collect this fast moving X-rays, and these are the substations. These are your substations where you can bring any of your instrument. If you are only interested in analyzing a particular sample, you can try to do that, or if you want a deposition chamber also to be transported, you are free to come and house your equipment here, study for a particular time, and then you can take it back. So, therefore, this is more of a central facility confined in a very large space, and many laboratories can be housed together, and the output is actually shared by everyone at the same time. So, therefore, it is a very sophisticated structure, and the dimension of this synchrotron facility is quite huge. We will look at one of the slide to understand this. We will see a short animation on what this facility will look like, and this is the inner side of the advanced light source, where you can see the inner core actually is generating X-ray from a linear accelerator, which is boosted up by the booster rings, and the booster rings are those which are having magnetic field, and once it comes out to the periphery, then it can actually go through several substations where this accelerated X-rays can be used, and this is how the booster actually works. And once it comes out, then it can be monochromatized and it can interact with the material, giving many informations that is needed, not just on the spectroscopy. In fact, even imaging of structures can be used using this map. Having seen the sophistication that is involved in this, I should also mention to you that this is a very selective facility that is available across the world, and here is a list of all the synchrotron radiation facilities that is available. It is also called as advanced light source, and as you would see here, many countries are really competing in this field. What is important to notice is the circumference of the synchrotron radiation source that we can look for in terms of meters, and then the energy that is generated. In this list you would see that the major players are actually in Europe and in US, and most of the facilities are housed in US. Therefore, this is a very costly equipment that has to be sustained, and one of the oldest, as you would see here, is from Lawrence Berkeley Laboratory, commissioned, and it was also decommissioned in 1993. Subsequently, a new advanced light source has come into picture, and then another one has been commissioned when the previous one was decommissioned, that is in 1993. You can actually look at the sophistications involved, the amount of giga electron volt that it can generate. These are some of the largest facilities in the world as of now, with a very massive infrastructure. One is in Argonne National Lab, and equally important are those in Germany, but we are also in the game in a smaller way. For example, if you look at Indian situation, we have two synchrotron light source, both are housed in Indore, and this is called Indus 1 and Indus 2, but you would see the circumference or the dia of your source is very small compared to what we saw in the earlier case. They have the circumference of 1000 meters, but we have fairly a very small unit, and the capability also is very less. Therefore, we can only study organic molecules using this facility. It is not possible to study heavier atoms. So, this is limited. Nevertheless, we are also in the map as far as synchrotron radiations are concerned. I am sure in the days to come there will be lot more progress, and we will improvise on this facility as a nation. So, this just to give you some idea about how these are localized, and there are also programs in our own country where we tie up with this advanced light source. Especially our country encourages lot of projects which can be returned to Trieste in Italy, where there is a synchrotron facility. So, it is possible for those who are looking for this spectroscopy to make a proposal and go and do a time bound research. But what we should also understand is that if you are really looking for in situ experiments, then we need to take the whole equipment and attach it to the beamline to study this. Most of the reactions that are done is all in situ, it is not ex situ. So, therefore, it is a very sophisticated way of looking at it. Now, let us look at the spectral features of this study and then understand a little bit about what we can learn. In the simplest case, that of a cupric, that is copper 2 complex, the 2p to 3d transition actually produces a 2p5 3d10 final state. So, when an electron is actually removed from 2p5, then what really happens to that? The 2p5 core actually which is created in the transition, this has a orbital angular momentum and which couples with the spin angular momentum. Therefore, it produces two states, j is equal to 3 by 2 and j is equal to 2 half state, and this actually comes out as a x-axis peak, which we call it as L2 and L3H. So, the intensities also are almost of the same order. These states are directly observable in the LH spectrum as the two main peaks. So, whenever we talk about LH spectra using x-axis, we are talking about L3 and L2, that is actually coming from a transition of p to d or s to p orbital. So, as we move across the periodic table, especially from copper, you go down go on the left side across the period, then you will see we create additional holes in the metal 3d orbitals. Let us take the case of iron, which is a low spin, and in low spin it is actually iron 3 is T2G5 Eg0, and therefore, this is your ground state, and in T2G5 Eg0 resulting in transitions to the T2G and EG sigma sets. Therefore, there are two possible final states that can happen when you are actually promoting a 2p electron through to either of these 3d orbitals. You can end up with a T2G6, that is what is denoted here, or we can end up with a T2G5 Eg1, and depending on these two, then you can actually get a peak like this, and this peak actually corresponds to the electron promoted to this final state, and this peak corresponds to electron that is promoted to this state. So, since the ground state metal configuration has one hole in the T2G orbital set and 4 holes in the EG orbital set, and intensity ratio of 1:4 is actually expected, as you would see here, between T2G and EG. Depending on the number of holes, the intensity of the peak also would vary in the ratio 1:4, but it is not always true. What will happen is this does not D6 excited state will further split in energy due to DD electron repulsion. As a result, you would see a much more complicated or a split pattern of these two peaks. So, these two peaks need to be analyzed rather more carefully, because there are other things that would compound with these structures. So, if you single out just the LH spectral component and try to look at it especially for complexes with a metal center, then your Tanabe-Sugano diagram will help you simulate theoretically how many LH spectrum can originate. As you would see here, you go from lower energy to higher energies region, the spectral features actually becomes more complicated. Therefore, more and more transitions are expected when you go to higher regions, and that is what you see here. Other factors like P, D, electron repulsion, spin orbit coupling, all this has to be considered when you try to simulate all the possible LH spectral components that are there. So, for ferric system, if you consider, there are theoretically there are 252 initial states and 1260 possible final states are possible together with the final LH spectrum. But what you would find here, despite all these possible state, it has been established that the low spin ferric system, the lowest energy peak is due to the transition to the T2G hole, and a more intense higher energy peak is that to the unoccupied EG orbitals. So, although there are several states possible, selectively these two states predominate over the other contributions which can actually be mapped, and you can see that from the L3H. Although there are split patterns, then you will be able to resolve which one is due to T2G and which one is due to EG. So, there are two things that we need to understand. Within L3 there will be two peak which will correspond to excitation to T2G or EG, and then you also have the L2. So, both this come into picture when we look at the excess. For a complex like this, which is a hexacyano iron 3 complex, you would see for a low spin this first peak corresponds to transition to T2G, and the second peak actually corresponds to EG, and then the third peak corresponds to the M level, that is your pi star. So, this is for L3 and this is for L2, and similarly for other transition metals you can see this is a inner sphere complex and this is a outer sphere complex, and in both cases you would see the spectral features are actually different. I will take one example from our own work on perovskite manganese and try to see how we have resolved some of the fundamental interactions that are happening within the unit cell using X-ray as a tool. As you know, perovskite manganese show interesting properties both in terms of magnetism and electrical conductivity, and this actually comes from a phenomena called double exchange, where you have from Mn3 the Eg electron actually goes to Mn4 plus Eg shell which is unoccupied. As a result, when this is actually transferring to the Mn4 plus core, and if it is ferromagnetically aligned to the localized T2G electrons, then this will actually become Mn3 plus because the electron has come here, and in the process this Mn3 will actually become Mn4. As a result, there will be a shift of this electron back and forth which is called as double exchange, and because of this double exchange phenomena that is happening mainly because of the presence of Mn3 and Mn4, then there is an interesting change from a paramagnetic to ferromagnetic state and from a insulator to a metallic state. So, two things happen when we try to initiate this electron transfer process, and this transfer of electron is given as transfer integral, that is Tij, which is proportional to cos theta ij. So, this cos theta ij is nothing but the angle that is made between these two ion cores. So, if this is going to be 180, then the transfer integral is going to be at its maximum. If this is actually going to be like this, for example, then this will get locked up at 90 degree. So, this transfer integral has to be theta has to be approximately theta ij 180 degree for a collinear ferromagnetism to operate. Now, in this situation you need both the case of Mn3 and Mn4, which is called as Zener pair, Mn3 plus and Mn4 plus, which is very crucial. So, I just want to emphasize that this Zener pair Mn3 Mn4 plus ratio is critical for this spectacular manifestation of magnetic and electrical conducting properties to occur at the same transition temperature. Now as I told you, Mn3 Mn4 is more sensitive, therefore if I try to alter this Mn3 Mn4 ratio, Mn4 plus ratio, then this double exchange or this strange occurrence of paramagnetic to ferromagnetic transition will be disturbed or it will be killed. As a result, this ratio has to be maintained at all cost. What we have tried to do is to put ruthenium into this site, either manganese 3 plus or 4 plus set, and try to see whether this interaction can still be maintained and how X-axis can be used to ascertain the interaction between manganese and ruthenium core centers. In the next slide we will see how ruthenium, when it is substituted into manganese sites, what will happen to the ferromagnetic interaction. From this cartoon in the top, you would see the plot of magnetization as a function of temperature, and this is a typical ferromagnetic transition that is happening. And during this transition, if you keep on adding ruthenium, as I told you, Mn3 plus Mn4 plus ordering is very important, and if little amount of Mn4 plus is also reduced, then immediately it will spoil the double exchange phenomena. And you can clearly see that the more ruthenium that is doped, the lesser the ferromagnetic transition, and the ferromagnetic transition is decreasing to lower temperature from room temperature. But what is interesting is even up to 40% of ruthenium that you dope into the manganese site, you can still observe a very strong collinear ferromagnetism, and this suggests that something else should be happening for this double exchange phenomena to occur or to sustain. Otherwise, even 10% of any 3D metal, if we try to dope in manganese site, will actually kill this whole magnetic interaction from a paramagnetic to a antiferromagnetic or to a insulating phase. So, this is the maximum that has been considered as the limiting composition for doping into manganesite, either by iron, chromium or any other metal ions. So, what is special about this ruthenium? Why, when ruthenium 4 is substituted, this long range ferromagnetism is still sustained? Why I am particularly emphasizing this here is, when you consider a unit lattice of manganese and ruthenium, for example. So, ruthenium 3 plus manganese 3 plus is there, manganese 4 plus is there. If you are increasing the proportion to 40, we are saying at every alternate position next to manganese, we are almost bringing another ruthenium. So, in a basal plane, AB basal plane, where we have manganese ruthenium, then we are almost evolving at a new perovskite phase, and this is not known or reported so far. So, in this case, what is that which is happening special to ruthenium doping compared to all other transition metals is the question, and how we can use X-axis to prove this point. As I told you from the previous graph, this long range ferromagnetism is also exemplified in the plot of resistance versus temperature. As you can see here, even with 30 and 40% ruthenium doping, you can still see this metal insulated transition on, and in these three cases metallic behavior is still seen. So, this is quite unusual for a ruthenium doping to show such a long range ferromagnetism. And not only to this 3D perovskites or 3D manganates, if we take any 2-dimensional layered manganese like this, in 2-dimensional layered manganese like La 1.2, Ca 1.8, Mn2 minus x, Rux, you actually have this collinear ferromagnetism which is confined only in the AB axis, and along the C axis it is not possible. Along the C axis it is not magnetically ordered. So, this is called as 2-dimensional manganese, where magnetism is confined only in 2 dimensions. But even in this case, as you see, if you put ruthenium, instead of killing the ferromagnetism, it is only improving on the ferromagnetic transition. In other words, with more and more of ruthenium concentration, you are able to push the Tc even to 20 Kelvin, which is a very unusual state. So, something very unusual is happening when ruthenium is doped into manganese, and you can see that the same case happens when you change from strontium to calcium, again increase in magnetization, and therefore, there is some thing that we can draw. There is a clear double exchange which is dominating over super exchange in the up to 20% of ruthenium doping, beyond which there seems to be some competing magnetic interactions, which I will discuss in some other module about the different magnetic phase. I will quickly go through another example of a simple manganite, La 0.7, calcium 0.3, manganese 1.x, ruthenium X. In this case, even if you keep on changing ruthenium, you can look at the L2 L3 H and see how the nature of this X-ray absorption peak changes. For example, we can actually try to compare the L2 L3 H with respect to strontium ruthenate Sr RuO3, because Sr RuO3, in this case the valency of ruthenium is proven. So, if you make a comparison with that, and you can clearly see that in the case of the ruthenium L2 L3 H, we can clearly see that there is a shift for above ruthenium 0.2 in this compositions. So, therefore, the ruthenium valency seems to be varying somewhere from 4 plus to some other valency, which is actually contributing to stabilizing the ferromagnetic interaction. And as you see here, the solid lines represent L3 and the open circles represent L2, and L2 is actually shifted. L2 is supposed to come here in the lower energies, L2 is supposed to come somewhere here, but it is purposely pushed here so that there is a comparison between L2 and L3 edges are made. So, what we see from this curve is that there is some issue that is significantly happening with the ruthenium oxidation state. Now, let us take another example of Sr RuO3. As I told you, in Sr RuO3, which is the parent compound, ruthenium is in 4 plus. Therefore, instead of doping ruthenium into manganite, we can now do a reverse doping where we put manganese into a known ruthenium oxide. So, in that case also you would see this is a ferromagnetic metal, whereas SrMnO3 is a antiferromagnetic insulator. Now, if you keep on doping manganese into ruthenium, you would see that there is a very strong ferromagnetic signal there. Even up to 70% we can see a ferromagnetic transition that is happening. There is a sustained Tc. This is very unusual. So, there is something happening not only in ruthenium, there is something happening in manganese also. So, what is that which is stabilizing ferromagnetism between ruthenium and manganese centers? This is what we can probe, and I am just listing out some of the parameters from the magnetic study. Tc, as you can see, because it is a broad transition, we can try to derivatize the curve and take the Tc. Even up to 50% of manganese doping, we still see a very clear Curie temperature, that is ferromagnetic ordering, and although the Tc is dropping, nevertheless it is not becoming non-magnetic. Now, to probe this, let us take the case of manganese L23 spectra, and if we look at the L2H and the L3H, L3H seems to be going through a very different feature compared to L2, and therefore if we carefully probe this, as you increase the concentration of manganese in strontium ruthenate, this particular C peak is actually growing in strength than B. So we can say that as we increase the concentration of manganese, then something is happening to the oxidation state of manganese. It may be either 3 or it should be 4, and that is why this particular intensity has grown very significantly compared to position B. And now let us take the same L23H for manganese core and try to compare this equiatomic composition, that is 50-50 of ruthenium and manganese, and make comparison between MnO2 and LiMn2O4. You can clearly see that this 50-50 composition is resembling more of LiMn2O4 compared to MnO2, because in MnO2 you actually have Mn only in 3+ state, whereas LiMn2O4 is a solid state battery material, it is a electrolyte, it is a electrode, and in this case manganese is present both in 3 and 4 state. So what we can say at this stage is, when manganese is doped into ruthenium or ruthenates, manganese is undergoing a mixed valence state similar to what we saw in ruthenium substituted manganites. Now let us go one more step and try to map the ruthenium L23 spectra carefully for all these substitutions as a function of x. As you see here, this x is equal to 0 is SrRuO3, and once you go up to 0.5 you can clearly see that there is a shift in the H for both L2 and L3, and also this L3 peak intensity is growing in intensity. So that clearly says that there is a shift in the ruthenium valence. So instead of 4 plus ruthenium, there seems to be a shift to higher valence state, because the shift is more towards higher energy. Therefore it should be ruthenium 4 to either ruthenium 5 or ruthenium 6. This much we can analyze from there. So let us take a comparison now. We will compare it with SrRuO3, which is 4 plus state, and here is another well known SR4RU2O9, which actually shows ruthenium in 5 plus state. Now if you compare the SrRuMn signal, it is neither in SrRuO3 state, which is 4 plus, nor in SR4RU2O9 state, which is 5 plus. So we can say clearly that the position of the 50-50 composition clearly suggests that ruthenium is in both 4 plus and 5 plus state. So because of that, we seem to be seeing a unusual ferromagnetic interaction. Now this can actually be compared to another well known well characterized system, which is LaSr copper ruthenate structure, which is a recently found ferromagnetic compound, and this particular one has ruthenium in both 4 plus 5 plus ratio, and as a result we can say that it is ruthenium which is undergoing a transformation to 5 plus state. Now to exclude the possibility of the crystal field contributions that can come other than or due to manganese doping, we can actually try to do a theoretical calculation also, where we can try to map the L2 L3H of both 4D4 and 4D3 states, 4D4 and 4D3 states. In this case we can try to change the Slater angle, which is nothing but your 10 dq value, and see how the L2 and L3 edges behave. And this is the case for 4D4, this is the case for 4D3 plus, 4d3 plus incidentally is your ruthenium 4 and 4d 3 plus, and in this case this is 4d4 plus, which is your ruthenium 5 plus. As you would see very clearly, not much change is happening, because only in this case you see the intensity of this A peak growing, but nevertheless you do not see any new features coming, because this is corresponding only to 0.2 electron volt. So 0.2 electron volt cannot substantiate for a promotion of 4 plus to a 5 plus state. So all we can say is the contribution is actually coming not from crystal field, but it is coming purely from the oxidation state. And for this calculation we have actually used a Hamiltonian. This Hamiltonian actually talks about the H average, which is coming from the crystal field, and then this is the one which is the Hamiltonian due to multiplet splitting, and this Hamiltonian MS is coming both from the LS coupling of your 2p electron, LS coupling of your 4d electron, and then your cubic crystal field contribution, and also this is from the exchange integral and the Coulomb integral of your electrons, that is from 2p to 4d. So this contribution is actually coming from your Coulomb and exchange integral, and this exchange integral Gij is what we call it as Slater integral. So all we can say from this calculation is that the crystal field is not contributing to this splitting, but this is truly coming from the oxidation state. Having said that, what we can say, what are the consequences of the presence of ruthenium 5 plus in this state, and how does it influence on the ferromagnetic state. So this is a sum up contour just to understand, having understood that there is a mixed valence state in manganese, and having understood that there is a mixed valency in ruthenium, how can we make a case for this? As you would see from a typical perovskite of manganite, the A axis and the B axis can be represented like this, and in this we told that this Eg electron can go to this site if it is ferromagnetically ordered when this angle is 180 degree. Now when we try to substitute ruthenium into this place, what is happening? Ruthenium 4 plus gets oxidized to ruthenium 5 plus, and in the bargain part of your manganese 4 plus is actually getting reduced to manganese 3 plus. As a result, now if you carefully look at the T2G Eg level of ruthenium 5 plus and T2G Eg level of your manganese 4 plus, the parentage of the T2G Eg orbital is the same. In other words, we are almost providing two pathways for this itinerant Eg electron to hop. One, it can go from here to manganese 4 plus, or it can go from here to ruthenium 5 plus, because as far as the T2G Eg occupation, it remains the same for both. As a result, even if you are going to substitute ruthenium to the order of 50%, you still can see a ferromagnetic ordering because of the isoelectronic configuration. Not only that, the coupled manganese 3 4 has a size which is comparable to that of manganese 4 5, and also both have a comparable redox potential. In this case, redox potential for this is 1.01, and in this case it is 1.13 EV. Therefore, because of the matching redox potential, whenever you try to put ruthenium 4 plus into manganese, immediately it promotes to ruthenium 5 plus. So even though ruthenium 4 plus is getting reduced to manganese 3 plus, you are almost creating another site for this electron hopping to occur. As a result, a ferromagnetism can be substantiated. So this is one case that I have tried to explain to you, where X-ray can without any doubt can resolve this issue, because it gives you precise information about the local structure, the oxidation state. As a result, we can propose a mechanism which is very unique of this particular compound. So with this I would like to finish, and there is a small animation that we can try to look at, and how the instrumentation is housed, and what are all the facilities that we can see. Here is where the yellow line signifies that the high energy X-rays are diverted to many places, and we can also typically see how this can be used in different substations. And these are the many beam lengths that we see in this advanced light source. A typical substation actually will have a lab as the lab that we see here. And not only we can look at the spectroscopy, as you would see in this particular lab which is using ALS source, we actually have a scanning tunneling microscopy which is being conducted, and this is specially on an isolated carbon nanotube. And here is a person working on carbon nanotubes, and the images are being seen here.